magnetic field. So what is rotating magnetic field? Rotating magnetic field is basically the movement of a magnet, which is rotation, that causes an electric current. Why are they important? Because this science is used behind many devices like fans and generators. Faraday's law. So what is Faraday's law? Faraday's law explains the whole concept of rotational magnetic field. Faraday's law states that a changing magnetic field induces an electromotive force in a conductor. So basically, it's saying that a moving of a magnet changes the current flow in a conductor. So Faraday in 1851, a man named Michael Faraday, who is also known as the father of electricity, performed an experiment in front of the Royal Society by moving a magnet in a coil which acted as a conductor and proving that the current changed as the magnet moved. In the same pace, the current also changed. This was caused because of the changing magnetic field that was caused by the moving magnet, and the current produced by this was called electromotive force. Magnets typically rotate. This is caused by a rotational motion in general application. I will talk more about that in the next slide. Basically, stator winding, rotor, and rotation. There's two main components in a motor, which a motor works using the rotating magnetic field. Rotor is basically, in basic terms, rotor is something that causes a magnetic field, and stator is where the current flows due to the changing magnetic field, and a rotor is rotated, and an electric field can also affect a magnet by changing it. Basically, it is like using a steel rod to move a magnet, and we can use a magnet to also move steel at the same time because they attract each other and repel each other. This force is used to spin a rotor or cause electricity to move. When electricity moves, this rotor, due to its magnetic force, also moves due to attraction and repelling of the magnetic force. And the same thing happens with electricity. When the rotor is moved, the electricity also flows, the current flows. And this is caused due to rotation, but it is more complicated than that. So I'll explain that in the next slide, where we talk about why we use three-phase current. We use three-phase current because when a magnet rotates, the stator stays stable. So, I mean, one of the phases in the stator where the coil connects to the rotor stays stable. So whenever the magnet rotates, the magnet passes through the north pole and the south pole and the neutral zone where there's no attraction or repelling. When there's south pole, the electrons, due to attraction or repelling, move in one direction, whereas in north pole, the electrons move in the opposite direction, and this causes fluctuation. And when there's only one phase and the magnet is rotating, this causes fluctuation of the electricity. So in practical applications, if this was the case, a light would be fluctuating constantly. And in three-phase alternating current, notice how it says alternating current. Same thing happens. It does fluctuate. Current does fluctuate, but it fluctuates in such a fast pace that we can't notice it. Because in every and of course in every 120 degrees there is a phase located. A coil is sticking in because 120 degrees, they have to be equally distanced from each other, and in order for them to be equally distanced from each other, they should be 120 because this is three-phase alternating. There's three phases, and so the electrons, every time the rotor is moving, the magnetic field is rotating, uh, one if one of the phase is moving in a negative direction, the other phase is moving in a positive direction, and the remaining phase might be in the neutral position and therefore might not have any current flow. And this is why the voltage of the net voltage of the current, uh, the net voltage of the stator is always at zero, because all of these uh, stators move at such a pace, all of these current flow at such a pace in each phase that they don't that when one is moving, the other is moving, and at uh, any given time, the total speed of the electrons, for basic language, flow at the same speed. The sum of the speed is the same, and this helps us have uh, consistent electricity and consistent rotation. So application of rotating magnetic field. Applications include usage of AC motors in electrical vehicles, EVs, and countless powering appliances, and industrial machinery. And then there's generators. Generators use AC generators basically use three-phase motors to generate electricity. So as the rotation is faster, the EMF, more EMF is produced and faster current, and that can be easily controlled using generators, uh, producing electricity. And other devices like pumps, fans, and magnet and MRI machines can also be have also used this principle to function. Advantages of rotating magnetic field. So these are highly efficient. This technology can be used for highly efficient power usage. We can transfer this energy to any of these. We can power lights, tube lights, to electrical vehicles, to fans, and many other applications, and therefore we can use this with efficiency without wasting any energy. Smooth operation. We can easily control the spinning and the um, production of electric current by controlling either rotation or the current produced, because the rotation and the electric current, the rotation of the magnetic field and the flow of the current are so in pace with each other that uh, controlling one will immediately um, control the other in the same way. So in this case, this is what causes it to be smooth. This is why uh, EVs tend to be more smoother than induction motor cars, where we hit brake and precise control. So EVs, so no, I'm sorry. So we can precisely control these, as I've discussed. We can uh, the rotation, the magnetic field, and the EMF produced are so in phase with each other, that we can, at any given point, if we slow down the current, the the rotation will also slow down at the same pace, or vice versa, and therefore we can precisely control these machines. So in conclusion, this principle of the magnetic rotation of magnetic field um, can be used in many devices and machines today, as I've already repeated, in everything, including from fans, lights, to industrial applications, to daily usage, EVs, and many other. And therefore, these are a very important. This is a very important contribution to the world. Thank you.